In this video, we take a broad look at the most characteristic reaction of carboxylic acid derivatives, which we call the acyl transfer reaction. Okay, so the overall reaction is depicted on the screen, and that's where we have a carboxylic acid derivative. As you saw in the last video, carboxylic acid derivatives have some group, I'm going to call it Z here, that's attached to the carbonyl carbon, where Z is an electronegative element. So the carboxylic acid derivatives react with nucleophiles. This should not come as a surprise to you because we've already seen aldehydes and ketones reacting with nucleophiles. Now, in this case, a substitution reaction takes place instead of an addition reaction. So with aldehydes and ketones, we saw the nucleophile would add across the CO pi bond. In this case, the nucleophile takes the place of the Z group. But the mechanism is more complicated, as we shall see, than a simple SN1 or SN2 substitution mechanism. Okay, this reaction is called an acyl transfer reaction because one way to think about this reaction is that the acyl group, which is depicted up here on the right, RC double bond O bound to something else, is being transferred from Z to the nucleophile. It's also sometimes called nucleophilic acyl substitution, where Z is the leaving group. This reaction is very common in many of the pathways in biochemistry. Okay, so understanding it now will help you make some sense of the jargon that you may run into in a biochemistry course. So I'm going to give you a couple of specific examples. One example of an acyl transfer reaction would be that an anhydride can be converted into an amide. Okay, so as we're seeing, one carboxylic acid derivative is being converted into another carboxylic acid derivative. So in this case, acetic anhydride reacts with two molecules of diisopropylamine to give diisopropyl acetamide, is the name of this product. And then the second molecule of diisopropylamine has to act as a base, so diisopropyl ammonium acetate is the byproduct that we don't particularly care about. The second example that I want to provide you with is the conversion of an acid chloride to an ester. So if we take an acid chloride, acetyl chloride in this case, react it with sodium methoxide, we will get methyl acetate, the ester, plus sodium chloride as the byproduct. So what I want to teach you now is the relative reactivity of the carboxylic acid derivatives. This is a very important diagram. The relative reactivity of the acid derivatives is that acid chlorides are the most reactive, anhydrides are the second most reactive, followed by esters, and followed by amides. Success in this unit depends on your ability to remember the order of reactivity of the carboxylic acid derivatives. But as usual, I don't just want you to remember something, I want you to understand why it's the case, and that may help you remember it. Okay, so the meaning of this, the reason why it's so important, is that a more reactive derivative can be converted into a less reactive derivative, but not vice versa. So as you saw on the last slide, we can take an acid chloride and turn it into an ester, or an amide, or even an anhydride for that matter. But we cannot take an ester and turn it into an anhydride. We cannot take an amide and turn it into an acid chloride. Why? Well, let's look at the leaving groups, which are conveniently indicated in red in the diagram. An acid chloride is going to lose chloride as the leaving group. Well, we already know that that's a really good leaving group. Anhydrides are going to lose an acetate or carboxylate if it's bigger as the leaving group. Somewhat stronger base than chloride is, right? And then an ester has to lose a molecule of RO-, which is a much stronger base. So as I already alluded to, this trend agrees with the basicity of the leaving group. Chloride is the weakest base, therefore it's the most reactive. And the amide ion, this is one of those unfortunate moments in chemistry where the five-letter word AMIDE means two different things. One is the conjugate base of an amine, and the other is the functional group that we are considering here. Both of those words, unfortunately, come into this definition. But the amide anion, Nr2-, is a very strong base. Therefore, amides are the least reactive. In case you want to know how strong a base is, you simply have to look at the pKa of their conjugate acid. Okay, so chloride is a weak base because its conjugate acid, HCl, has a pKa of -7. Acetate is a moderate base. Its conjugate acid is acetic acid, which has a pKa of 4.75. Alcohols are the conjugate acid of OR-. OR- is a much stronger base because alcohols have a pKa of 16. And then finally, Nr2- is a very, very strong base because its conjugate acid, a neutral amine, has a pKa of 38. Okay, so in this slide, I want to look at the general mechanism for an acyl transfer reaction. We will look at a specific example in the next video. So nucleophilic acyl substitution is a two-step process. In the first step, the nucleophile attacks the carbonyl carbon and breaks the CO pi bond to put a negative charge onto the oxygen. This is completely analogous to what we saw in the reactions of nucleophiles with aldehydes and ketones. Okay, so the intermediate that you get here, we call it a tetrahedral intermediate because the geometry at the carbon that used to be the carbonyl carbon is now tetrahedral. It was trigonal planar when it was a carbonyl carbon. It is now tetrahedral. However, in this case, you have a leaving group, Z. So the electrons on the O- reform in the second step the CO pi bond and kick out Z as a leaving group. Now, this is going to happen because CO double bonds tend to be quite stable. So this loss of the leaving group step will occur if a leaving group is present. In some cases, if Z is chloride, this is really, really stable, or even if it's acetate, because you're giving off a weaker base than you would have at the tetrahedral intermediate. Okay, so look at this mechanism. If you need to, pause this video, go back and look at it again, because this mechanism needs to be firmly imprinted on your brain as we continue to go through this unit. Most of the rest of this unit are just specific examples of how this mechanism is put into practice, along with some extra proton transfer steps here and there. Okay, why does this not happen with aldehydes and ketones? Aldehydes and ketones, as I've said, undergo simple carbonyl addition with nucleophiles, but they have no leaving group to expel from the tetrahedral intermediate, so it stops right there. If you were to look at the tetrahedral intermediate that you get from addition of a nucleophile to an aldehyde, the thing that would take the place of Z in this particular intermediate would be H-. If you have a ketone, Z would be R-. Well, H- and R- are both very, very powerful bases and very poor leaving groups. How do we know this? H- is the conjugate base of H2, and H2 has a pKa of 35. R- would be the conjugate base of an alkane, and alkanes have a pKa of 50. So that is why you do not get the nucleophilic acyl substitution mechanism with an aldehyde or ketone. You just get simple carbonyl addition. When you have an acyl carboxylic acid derivative, where Z can be a reasonable leaving group, we're going to get the addition-elimination mechanism. Okay, so in the next video, we will look at a more specific example of this reaction and go through its mechanism in detail.